Today we are going to discuss on a very important topic, and that is the critical role of hearth management. Hence, we are diving into one of the most critical yet often overlooked aspect of blast furnace operation. Many times it happens that everyone is focused on the casting and the production without much focus on the hearth profile and hearth temperature trends. So the hearth is most important. It is not the top gas or the Bosch, but the silent foundation of furnace that control your entire campaign life of the blast furnace, as well as it associated with safety in a specific manner. So neglecting it can cost millions of rupees, and also it leads to catastrophic failure. So we can say that it is very important. So how do we keep its health well, it long lasting, its campaign extension, and consequently leading to low cost of hot metal. So let's explore all these unanswered questions. First of all, let us have a understanding on Hearth campaign stages. As it shows, the information in the slide already well captured the Hearth life, which unfold in two stages, that is stage 1 and stage 2. Stage 1 is normal operation with minimal concern, but the most important thing that operator needs to know is that once temperatures cross the critical limits, and what is that limit? That limit is 450 degrees centigrade at 500 mm inside the furnace. 450 degrees centigrade at 500 mm inside the furnace. Enter stage 2. And this is the most important stage where we need to take some action. That's when campaign extension starts. And this is the point where campaign extension start. That's why without timely action, risk rise sharply and failures loom. So, identifying this transition, that is stage 1 to stage 2, is very important. These need to be traced. So, this transition is key to safe operation. Now, coming to the damages in the hearth. What sort of damages? So, let us discuss the key wear mechanisms. And as usually, we can say that we are going to uncover what destroy the hearth. So especially through the mechanism, either the thermomechanical or the chemical. So we will discuss the thermomechanical wear first, which associated with a combination or a single one, like it is a stress cracking, a spalling, and hot metal erosion. Many times it is a combination of all three also. So these phenomena especially occur at a very high temperature like 1150 degrees centigrade, and this is a very critical boundary. That is what we are termed it as a 1150 isotherm. So during no skull operation, particularly this boundary becomes very, very alarming and important. On the chemical side, as you know, we face a silent killers like alkali attack, the oxidation, and and it is not a small, it is very dangerous, and that is carbon deposition. That is carbon deposition from carbon monoxide disintegration is a really it affect in a tremendous way. So these mechanisms work quietly, quietly, but they can create severity of damage in a very intense manner. It may be very severe, but they severely damage the refractory over time, and hence monitoring of each of the effects gets reflected in thermocouple strains that need to be assessed very carefully. So here we come across a one finding that hard design matters, and each one of us to choose very wisely that in our contest which design suits best, because this design also helps in extending the campaign. So we can say that all hearts are not created equal. Everyone has got their own preferences. But a standard hearth rely on carbon block with a spray or casting uh, iron cooling system. It's basically a combination of a carbon refractory with a cooling system. And wherever this combination of these two works well, so they are functional but limited in redundancy. Now let's talk about the copper stave hearths. Copper staves hearth cool better but may deform under stress. So it has also a sort of a constraint. So then what is the best? So we need to introspect these aspects, especially in our contest, that what is the best. So safety hearth with a graphite layers, these rapidly freeze hot metal and offer resilience. Of course, we cannot formulate that this is the best. We need to see in our contest which is the best. So such type of combination has proven to extend the life beyond 50 plus years. Thus, design impact everything. Now, it is all about monitoring our hearth. In what way we should monitor, that is all important. And for these, we need to see our early warning system, because for any action, system must guide what sort of action is needed in the heart. And monitoring is possible, and monitoring is our eyes and ears. So old system, as you must be knowing, old system has just 10 to 50 thermocouples. Even though they are not sufficient in today's time, not enough. But if we see the modern setups, which have got a at least more than 150 and uh, up to 250 thermocouples is there, because the horizontally, vertically they are aligned, correlated. So this densely covered critical areas like taphole and bottoms. These are also not giving a only campaign information. They are also operational information are coming from there. So tracking the 450 degrees centigrade and 1150 degrees centigrade zones, our early morning and actual wear line can be traced. Hence, so many thermocouples are there, so many tracking devices is there, but there should be some thumb rule, there should be some key. But despite all these, beware of a misguiding brittle layers, especially many times this thermocouples, CFT analysis, simulation and model and level 2 correlations of these flux slices on the carbon brick fail due to intermittent brittle layer formation in the carbon brick. And in view of this thing, in past also many blast furnaces did core drilling, and this we can say this is a, a reality check because these systems, these thermocouples guide, but many times it has to confirm. And for this, that we can say that when in doubt, drill it out. So when we have a doubt, we can go for such type of things like core drilling, which give real samples of refractory thickness and brittleness. So we can say that especially after 10 to 15 years, we can also confront this activity. We should do this activity to match and see what our thermocouples are talking about, what sort of trend they are thinking, and if certain spikes, temperature spikes are there in those situations, we must do this. They help plan repairs, validate thermal models, and detect carbon attacks. Drill location may be two places which are very vulnerable. One is the taphole area, and other is the elephant foot profile in the corner plane, where we can have a core drilling to see whether this temperature spikes which is shown in level 2 or level 1 or thermocouple straight readings, they are having got a they are they have a matching with this code drilling outcome or not. So it is code drilling is supposed to be the most uh, con- confirming exercise that need to do after 15 10 to 15 year band of the furnace. So you can say that this is to be confirmed. This is a confirmed test. So now the question arises that what sort of uh, repairs that can be extended during the furnace, whether furnace is to be taken for stoppages or live. So it is not like that all the time. It need to be only stoppages is required, but it depends what sort of repair we are undertaking. For example, many of the repairs at the taphole area or the taphole bricks, it need to furnace is on live, furnace is live, and at that time we can apply with our special type of clays which are pushed through the taphole to take care of this carbon peak around the taphole. So there we can put on this furnace live. But at the same time, if we have some certain major repair, especially in the carbon prick in the below the taphole area, and if it is the repair is massive, then it is not safe to go for a live. It need outrages, and this can uh, taken as a corrective measure to take shutdown and then repair. Apart from this, many intermittent corrections also we can do in view of this hearth care, as a like reduction of PCIs and plugging of the tuyers, and we can say the casting management practices, all going to help us, especially in extending this uh, this hearth care. So we can say that safe thickness and repair always trigger. So these we can say that uh, what is this safe thickness as it is shown in the graphical trend this slide. So we can say that standard carbon hearth, that is for carbon hearth, 500 mAs is our go no go zone. So for graphite line hearth, just 150 to 300 is often safe, and thanks to rapid freezing phenomena due to intensive cooling system which takes care of the such carbon bricks. Thus, it is we can say that it is about a design, it is about a selection of material. All this helps. This also arrest our activity of crossing the 1150 isotherms or losing graphite, which is going to act immediately. So such type of things we need to take as a major corrective measure to take care of our carbon hearth. So finally, we can say that then what is the final thought? So we can summarize our final thought as a one line that let us build our hearth strategy. And for that, we can say that wrapping up each furnace is unique. Using dense thermocouple, build a hearth history models, segregating all the data information over a period carefully, and finally verifying all this with the code drilling actually set a clear operating limit. Hence, we need and we need to be ready with a very clear repair strategy, and above all, the most importantly is train your team for this hearth awareness, which is very important, because unless until team members are aware about importance of it, things are not getting monitored properly. So that's the foundation of safe long campaigns. Thank you.